Is it okay? Yeah. So welcome back to post T session of this day 4 of this GAN course. So as we discuss many aspects of fluorine chemistry, one important aspect is also characterization of compounds. And for that, we are going to discuss more about fluorine 19 NMR. So for that, we have today Srinivas from Jewel India. He's an application expert, and he is located at Bangalore. And right now, you all know that we have two Jewel machines. We also have Sandeep and Dr. Archana, who are the experts who operates our NMR. So what I asked Srinivas to give a brief overview about NMR, because I just want to mention, Srinivas, that we have there's some problem. We have first year MPharm students, mostly who just started learning NMR. So I try to see little briefly if you can give a brief info about basics. I think they have completed 4 to 5 lectures so far in NMR. Then based on whatever you cover, then I will also cover some basic aspects in the evening today or sometime tomorrow. So Srinivas has a very good, he's an organic chemist, so he understands small molecules, and it is very good that an organic chemist, and then after his masters from after his masters he joins IISc Bangalore, and he was taking care of the NMR facility over there. After working there for 3 years, then he has moved to Jewel. Okay, and then so with this background, I will also request Srinivas to give a brief background about himself, because about his trajectory, so that students can have an idea that maybe that could be another kind of a possible job prospects. So with this, I request Srinivas to give a talk on fluorine NMR.
Good morning, all. And first of all, thanks, sir, for calling us for this involved into the intense workshops, mainly on the synthetic backgrounds. And again, of course, we are the manufacturer of analytical instrument. It's a good opportunity for us to be interact with the young mind and the experts of synthetic groups and understanding your problem and what the spectroscopy techniques can give us solutions. And some of the techniques may not be known by the users, or some may be using very routine experiments simple like proton, carbon experiment, or maybe a simple 1D experiment based. There are maybe a advanced experiment, and there are something like interesting experiment which is unrevealed by the chemist. So the reason is, being an NMR spectroscopist, if we talk about that, we have 1,000 pulse programs available in the library. But it is not untouched. It's all are one by one added and are revised based on the problems. So, and today's, as for the focus, we are talking about only fluorine nuclei and in NMR spectroscopy. Okay. Well, let me introduce myself, because anyway, sir told me that about it, but just want to give introductions about history about that. So, I did my master's in organic chemistry. So it is in 2009, it's way back. And then afterwards, I joined NMR Research Center, IISc Bangalore, as a project fellow. So I was with the lab for a year. Then the last 2 years, I joined with the Professor Surya Prakash. He is working for the small molecular research and mainly onto the chiral discrimination. I mean, the big task for all the chemists is that when you have a mixtures of enantiomers, when take an NMR spectra, it won't give any separate peaks. Everything is merged up. How to solve that problems? So in that categories, I have worked through years on that case. So we have a couple of pulse program developed also. And all we know that we have 3 methods: lanthanide shift reagents, or we have solvating agents, or divertizing agents. So with the same methods, we can do it, or pulse program wise, we can make any modifications. We have done things on using a diffusion experiment. We have utilized that experiment to separate the chiral centers and these things. And in 2013, I have joined Geol India as an NMR application specialist. So it's close to 12 years now with the Geol. So we have a lot of opportunity to interact with our global application team, and we meet with the different application group and working on the different problems. So this is my history about NMR side. So totally I have close to 15, 16 years of NMR expertise in this. Okay, let me, this is my introductions. Let me start with my talk. Okay, so you are already having the 6 days of continuous intensive workshops on the synthetic and molecules, understanding biological activities of fluorinated molecules one. Now, we all know that synthesis is one part, and after synthesized one, characterization is very, very important. Whatever you do it has to be identified properly and reported, and you have to make a not only qualitative ways, you have to make it a quantitative methods, you have to prove that this molecule is correct. So in this sense, we have a spectroscopy techniques, we have a different techniques, like we have UV visibles, IR, all these things, and we have a mass spectrometry also to identify that, right? So in that, NMR spectroscopy plays a very important role, because this comes with the where the NMR is mainly onto the nuclear interactions. So when the nuclear is talking about that, you can easily identify it. It's related to all the chemical environmental sites, right? So the NMR spectroscopy is a very, very important spectroscopy technique for the characterization things. So this will be the characterization methods. We are now discussing about that. So before I start with the fluorine NMRs, let me give some brief introduction about the, or I can say, just want to show how NMR spectroscopy is so potential in the chemistry research part. Okay, it has a wide variety of applications in. We take it from the entire scientific research wise. So let's give a simple one. The first we utilize for the chemical structure and dynamic studies. Okay, you have a molecule, then identify whether my synthesized molecule is correct. Identification of 2D structures and 3D structures of that. And even when you have molecule and you have a targets, how it is interacting, dynamics of identifying the molecule is also important. That part also it can be done with the NMR spectroscopy. We have a different experiments and different nuclei to measure that. The beauty of NMR is that it is not one nucleus, whatever the elements available in the periodic table all has isotopes, then you can do the NMR measurement. That's interesting things. You can do the mainly chemical characterization dynamic studies. Then you can utilize for the macromolecular studies. Okay, you have nanotubings or big molecule interactions, molecular radii identification, size of that also can be identified through the NMRs. Here again we do it with the NMR active nuclei. We do a proton measurement experiment. Maybe it may be 1D or it may be 2D experiments to identify the interaction between the big macromolecule and with a small molecule. Or if you want to identify the radii of that, we have a special experiment called the diffusion experiment. DOSI we call it is. You can use that one, identify the diffusion coefficient. From the diffusion coefficient, we can go back to the radii. It can be identified with these molecules. This also can be done with the NMRs. And now we have, it comes with NMR, it comes to food industry also. It's very, very important now. In food industry, the problem is adulteration, right? So when you talk about any products, like there may be adulteration. If you take a honey, juice or cheese, anything. So this adulteration process also can be identified through the NMR. How it will be done? Again, it's with the NMR spectra. You have a compound, maybe a food has some materials like amino acid or something else, you have molecule. Along with it, if you have impurities peaks, it has a different chemical fingerprint regions. Identify, matching with the spectra. You can identify that, so with that it has impurities. If it is adulterated, what percentage of adulteration has been done? There are some databases required. You can do some statistical analysis, importance like PC analysis, PLS analysis. The different methods of statistical analysis can be utilized to the food industry side. So now the recent trend in India also, the government has imposed the NMR spectroscopy is the right technique for the honey profiling. Earlier it was not, that was maybe the 5-6 years back it was started with this. Now even the TV commercial advertisement, they were showing that NMR spectroscopy is the screening process used for the honeys. And there are, if you see that when it came, maybe we have many manufacturers make of the honey, right? In that only 1 or 2 manufacturers qualified that is authenticated honey process. So, and drug discovery sites, it is again all this step of process, identification of the molecules can be done with this case, interaction studies. Biomolecular application, of course, this is another interesting areas. But biomolecules consist of the carbon, proton, carbon, nitrogen based chain system, okay. We have a multiple experiment, a multi-dimensional experiment. You can correlate that. A small molecule, one dimensional, two dimensional is good enough. If your molecular size is big, you can have a 3D NMR, 4D NMR, you can make a correlation part. You can do that identification. So that's a biomolecular structure identification. Petroleum product, again it comes with a molecules or mixture of compounds. It maybe you can identify with the what is the naphtha content in the petroleum product. And petroleum industry has different segments. You have crude oils, diesels, petroleums, catalysis studies can be done with this. All these areas NMR utilized. You can do a simple carbon measurement, or you can do the carbon based quantification, you can do that. And proton based quantification, you can do that. And by using the spectra, you can identify what is the naphtha content, what is how much aromaticity is present, how much aliphatic compound group is present, you can identify it. And interesting fact is that it's not only, it is a high resolution part, I'm talking about NMR. Now, in case of a low field also, no oil well, you have the oil wells, how to identify how much percentage of petroleum content is present. You can send the portable NMR in the oil well, there you can identify this percentage base. How they do it is based on the relaxation, T1 relaxation base, the different methods to identify that. There also NMR is utilized. And agrochemicals, again this is chemistry, there are different kind of nuclei, you have phosphorus, NMR you can do it, you can utilize for the silicon based experiment or sulfur, different type of NMR can be done. Toxicology, again it is heterocyclic compounds, you have a nitrogen based compounds over there, you can do the nitrogen experiments. And you can do with the proton nitrogen correlation experiment also, you can do that. And we have all the areas. Now the very interesting fact is now the battery applications, right? The battery is another booming subject now, right? So in the NMR research we have reached where till we can do operando measurement. In situ battery operation can be identified. So while doing a charging of battery, what is the electrolyte diffusion happens with ions, how much that can be identified. So in battery we have three electrodes, anodes, cathode, electrolyte. All three materials are made up of the chemicals, right? You can do the NMR measurement. When you have a solid electrolyte, you can do the solid state NMR. You can do sodium based NMR, you can do it. If your battery is lithium ion measurement can be done with that. How lithium diffusion is happening, that can be identified in solid state. If you have solid electrolytes, simple, you can measure that ion diffusion, dosy experiment, and different method of experiment to do it. You can do a battery application also, you can do that. While charging, discharging one, we have made a probe such a way that in the probe itself you can load your battery assembly, you can supply the voltage current. Then you can identify how these ions are diffusing, so the variations of the ions that can be identified with this. So a lot of applications can be done with NMR spectroscopy. So okay, let me go to start with this understanding. Now first question comes, what is NMR? It's nuclear magnetic resonance spectroscopy. It's a spectroscopy technique. Extensively utilized for the chemical substance characterization and in non-invasive techniques. Here whatever sample taken back for the further reaction. You can do that. There is no distraction. If you take a mass spectrometry, you cannot take back the sample, it is gone. In NMR not like that, you can take back the samples. That's why we have a big application called MRI. So MRI is also based on the NMR principle. The sample is human body or something, you can send it inside, that's what we do it. And you can do most element can be identified. You can do with the proton, deuterium, carbon, phosphorus, this all the living organisms, whatever you have it, all the elements, this is available, it can be identified. Even oxygen, nitrogens, this can be identified, all that in NMR. Molecular dynamics, reactivity can be identified. Let us understand a little bit about that. I will not go in detail about how spectroscopy works because you already have some coursework, maybe some fresh students might require some brush up, whatever learned from the graduation. So in NMR, it's basically nuclear magnetic resonance. So when you take a sample, every molecule has the atom. Atom consists of the nucleons, right? So in the nucleus, if you have the nucleons, combination of odd number of protons and the neutron, it's act as NMR active. There should be some spin value. If you have a spin value, that is NMR active. Okay. So now there are like example like hydrogen, it's only one protons. Carbon, again you have the neutron and proton, but it's odd combination. Again, so your total atomic mass number will be a 13 is active and 12 is a proton numbers. But when you talk about the C12, it's even combinations. That is not NMR active. Okay, so the spin values where it becomes 0, this is basically resultant spin angular momentum of the nucleons. If it is a 0, those are not NMR active. Where spin value is present, those are NMR active. So what happens, it lacks, like when you have a spin, of course there is a fundamental property called magnetic momentum. So when you take it in the gyro ratios, the top equivalents, when you take it in the earth magnetic field, it again rotates. That is a lump position. Now this tiny magnet, if you place it in the NMR, any external magnetic field, okay, then it has there's a torque presence. One is I value spins, just imagination, and again when you place in magnetic field, it feels as torque, okay, because of the external fields. Then there is a precision, that is called the Larmor precision, okay, that varies with the nuclei to nuclei. Now this is an example here. When you sample outside the magnet, it's all randomly oriented. Well, it's randomly oriented. So, sorry, it's annoying noise. It's a randomly oriented nucleus. Of course, molecules are movements with this. When you place it in the magnetic field, there is a force. Okay, some will be aligned to the magnetic field, some will be opposite to the magnetic field. Again, depends on the energy state, depends on the I values. If you have a half, there may be 2 energy state. If you have 3 by 2, a different energy states will be there. Okay, so energy. So this is external magnetic field. Now here again, so this is energy states. This energy gap is very small, very small it is. Okay, and so the population difference is also very small. So when energy gap is very difference is less, the nuclei can present in the ground or the upper state. The difference is very less. Now this energy gap is exactly matches to the radio frequency. Okay, so then only this will talk. When you apply the radio frequency onto this, then there is an excitation process happens. The lower energy state nuclei goes to higher energy state, higher comes to lower energy. There is excitation. This is the one. Now just the difference talking about it. If you take high field NMR, now the difference is very less. You can take it about almost of, this is almost 1 gigahertz magnet. The difference between the population is almost 10,000 or nuclear wise. It's a very low sensitive technique in the cases. Okay, this is the basic principle of how NMR works. Now again, the energy gap depends on the nuclei. Nuclei has a property called magnetogyric ratio that depends on the variation happens in these cases. Now this is how magnet looks like. So you have two excellent in system here. One is 500 MHz NMR, another one is 600 MHz NMR instrument. So this is how it looks if somebody's first time doing the NMR. You can see this is a magnet, superconducting magnet, and it is the spectrometer and is a computer. So now there is a probe, your whole RF assembly is sitting here, that will be loaded into the magnet downside, and your RF coil is present in the probe and sits in the center of the magnet outside the magnetic field. Okay, the whole entire magnet phenomenon happens over here, NMR phenomenon happens over here, and everything will controlled by the RF assembly. This is called the console or a spectrometer. Then it will be here. So whatever the supply will be based on the current has the parameter called the amplitude frequency phase that will applied, and when it comes back to that, it comes as analogous signal. But as a computer cannot read the analogous signals, it has to be digitized. So it will be digitized, and the conversion method called the Fourier transformation from the time scale to a frequency domain, that will happens over here, and you will get a spectra out from this. Okay, this is how the NMR works in principle. And the field relations. Now as I mentioned, so the energy gap is too low, the energy sensitivity is low. How can I increase my sensitivity or the field relation? If I increase the magnetic field strength, energy gap increases and increases in power. When energy gap is increases, there is a population difference is increasing. When population difference increasing means you are increasing signal to noise ratio. That's why people looking for high field NMR for the bigger size molecule. If you have protein or something where it cannot be resolved in the lower field, it can be resolved in the high field one. There are two problems in NMR. The one is a resolution, second one is sensitivity. To solve that, okay, so we go to high field NMR. Now here's an example here, a small molecule, ethyl benzene. So if you record 60 megahertz, all protons here aromatic big single peak because resolution is too low. Then go to field higher and higher, everything resolves out here. Your metaproton, ortho, paraprotons get resolved out. Okay, the resolution can be achieved. So that's why the biomolecule has a big size, right? Lot of protons are present. To resolve that, you require a high field one. To get the high resolution, high field NMR. And sensitivity, second part is that. Again, so when you get a samples to increase the signal to noise ratio, the two way to do it. One is adding more concentration or more samples. But that is not possible for a biomolecular case or something like when you have very precious samples. If you have inorganic material, you can get a 1 mg, 1 gram samples as okay. But when you go to the biomolecules, getting 100 millimolar concentration is very difficult for them. So how can I boost it that? The only way is the sensitivity has to be increased. There are some probe techniques called the cryo probes we have, and different type of probes are available. Now his sensitivity problems. So now you can see using high field NMR, you can increase signal to noise ratio also and resolution, both can be improvised. So they just want to summarize on this point, to NMR is insensitive, very low sensitivity. To increase the sensitivity or low sensitivity resolution, you require high field NMR. Okay. In most of the kit, in general application, if you have 400 to 500 megahertz NMR, you can run the molecular size of around 2000, 3000 molecular sizes you can easily handle. But if your molecular size is increasing higher and higher, it becomes like 5000 or 10 kD, 15 kD, 20 kD, you require high field like 600, 800 megahertz NMR with combination of the cryoprobe. Okay, this techniques. Basic. And next comes to that, now let's go to the, now this is, I'll not go deep about the instrumentation side, let's go to the application side now. So NMR, when you get NMR spectra, these are the parameters can be obtained. The one is chemical shift. What is chemical shift? It's a frequency scale basically, okay. All based on the chemical environment, you'll get individual separate peaks. There is a chemical shift. And spin-spin coupling based on the neighboring effect. Suppose you have some in NMR, all nucleus are active. So I have proton here, I have proton here, the proton can interact, talk to each other. So then makes it peaks, supposed to come a single, it may be doublet. Or that depends on number of nucleus present, big splitting patterns. So there are spin-spin couplings. And that gives information about the neighboring environment. Then intensity of signals. Again, intensity of signals gives a number of responsible nuclei. Suppose you methyl has a 3, and if you do area under the curve, if you do the integration for that, that gives a number of protons, number of carbons, number of phosphorus. And relaxation is another important parameter, T1, T2 relaxation, spin lattice and spin, the transverse relaxation part, both. Okay. So this gives information about the molecular size and molecular natures. Okay. So that will varies, T1, T2 will varies. And NOE, overall effect, so the spatial correlation can be obtained. And dipolar and quadrupolar couplings are based on the nuclei. If you have a high spin values, this both are comes into the picture. Okay. So now importance, now how NMR utilized for the pharma industries. Now pharmaceutical industry, you can do API measurement, you can do that. Okay. Then you can do the quantification of impurities also can be done. And if you have excipients and API mix up. Okay. So then if you want to separate these two, virtual separation, of course, it's not a physical separation. You can separate the peak. You can identify the excipients and the API. Suppose you have two APIs are present in over there. If you want to identify that's how many APIs are present, you can do the experiment. You can separate the components. Or you have something that can be identified. This is one thing. And analysis of all the drug product, drug polymorphism is very important here. So synthesizing, then you have solid state, you might have a dimer formation, trimer formations or interaction between that can be identified. Quantification of purity, co-crystals, salt formation, solvating properties can be identified through the NMRs. You can do that. Okay, so now let's go into the fluorine NMR. So, but I don't think so this slide is required because already you have detailed talks for this. So fluorine has a very important role in the chemistry research. It can give add-ons to the different properties like polarity, acidity, reactivity sites, and it's widely used in pharmaceutical, agrochemicals, material science application can be done. And the fluorine important thing is a very strong electronegative atoms, okay, and it has the very smallest substituent replace hydrogen nucleus. When I have fluorines, it can have a steric effect different, polarity difference. This is gives interesting things. In concern to the NMR, okay, let's drug molecules, you have seen that most of the drug molecule have a fluorine nucleus. You can see that almost 25 drugs are containing the fluorine ones and different places utilized. Now when it comes to the NMR side, how fluorine will be utilized, how the fluorine is active. The interesting fact about fluorine is a spin half nuclei, okay, I value. When the I value is very less, then the measurement becomes very simple. Spectra becomes more simplified. That's why proton, carbon spectra are very simple because I values are half. When you go to boron NMR, analysis is not this easy because 3/2, that is spin value is higher, then the quadrupolar effect will comes up in the picture. So the spin is very easy to measure that. Interesting fact is that abundance, it is 100%. It's like a simple like a proton only. The measurement is very high measurement easily. And comparing the relative sensitivity versus proton to a fluorine, you can see that it's almost 0.83%. This if you take one is highest and this is one. Next highest abundant nuclei for the measurement sensitivity wise is a fluorine compared to proton one. Now you can see that property wise. So here proton is one of the most utilized nuclei for NMR studies. because of the abundance and the I value gyrometric ratios, and this is the main things. Second one is the carbon will be that carbon is a less abundance, of course low sensitivity, but when you have low concentration, low mixture concentration has a difficulty to measurement, so on. Nitrogen again even lesser abundance. Now nitrogen has a two isotope, nitrogen 14 and 15, correct? The 14 problem is a quadrupolar nuclei. The measurement becomes a very difficult and sensitivity lost over there. Okay, peak becomes very broader. It goes buried under the noise level. Okay, that maybe now the recent techniques has been improvised for the enhanced sensitivity, and those different techniques can be utilized for the make it a better signals. And the abundance is very less. And here good part is frequency separation is a larger one. So when you have different molecules can be seen separate peaks over there. Okay, but in case of proton, the ppm separation is 0 to 13 ppm. All peaks comes in one place. It may be merges. And a fluorine case, the spectral chemical shift range is wider. It's close to, you can say that 350 ppm range, plus 50 to minus 300 ppm. So if you have make a small changes in the molecule, still the peak becomes separations, well separated peaks. Okay, so that can be identified in this one. This is an interesting fact about a fluorine. You can utilize for your most of the research part. So chemical shift, as I mentioned, you have different type of molecules are present, then it spreads over that. Make a small changes. Now you have one fluorine over here, so the two protons, the chemical shift is here. Now we just removing one of the proton, introducing another fluorine to this, chemical shift, look at this, the huge difference, that is shielding effect and de-shielding effect difference variations, the larger variations. Now another important thing is, now simple fluorine measurement is okay. But now when a fluorine is present in my molecule, then if I measured another nuclei, carbon nuclei, this fluorine makes a problematic. As like a proton only, highly abundance, right? It interacts this. The problem is when the fluorine is present, now a molecule of fluorine have carbon attachment. The fluorine and carbon coupling is very, very strong. Now look at this. Here is a coupling constant values mentioned for that. Now if you have a fluorine couplings, there is no direct bonding, there is no molecule like that fluorine present, it may be two bond, the two bond coupling is 400 Hertz. Okay, it looks like if you have 400 megahertz NMR, it looks like 1 ppm difference almost, the fluorine coupling values itself. If you have two coupling, it will be two larger one. So 3 bond will be a 150 Hertz. The problem here it is I can see fluorine carbon coupling. The 1 bond coupling goes to 150 Hertz to 250 Hertz. It looks like half the ppm difference, almost of 1 ppm difference. Now when I have molecule, the fluorine is present, it makes it complicated. When you record a carbon NMR, it's because two separate. You will get an ambiguity, difficulty that whether it is a two separate peak or whether it is from the coupling from the fluorine. That is a big problem. So unless you remove the fluorine couplings. But as a practical you see, when you go to instrument, proton and the fluorine goes in the same channel. Okay, instrument, let me explain a little bit about this. Two channels you have. Channel 1 you have proton, fluorine, another channel goes for the broadband. Okay. Now if I want to do I can do only one decoupling one time, not simultaneously, I cannot do that. Okay, because both frequencies has to go together, right? Difficulties. Now in my molecule I have carbon has a coupling from the fluorine and the proton together. If I do a proton decoupling, the fluorine coupling will comes into the picture. Peak becomes separated. So that is a little bit difficulty task. So for the chemist, and sometime you'll get a and problem is splitting, signal to noise get reduces huge. That is a problematic, especially for the CF3 groups where I have the junction carbons, where the fluorine is present. That carbon will not come up easily because of the one is a fluorine coupling, second one is the splitting patterns to I. That is a big difficulties. So this is the coupling patterns. So the two bond coupling is very high, and fluorine and carbon is 10 to 40, and the 3 bond coupling is 0 to 10 Hertz. And the phosphorus and fluorine coupling is again is a very high couplings, but these are the very less. Here not much difficulties because you may be having one phosphorus or two phosphorus in the molecule, then easily can identify with this. But only problem comes for the carbon sides, where so many carbons are present and one fluorine is present. It can go to 1 bond coupling, 2 bond coupling, 3 bond coupling. It can go to the longer range couplings. That makes a complexity in the spectra.
But then the 13C abundance is also pretty low.
Yes.
But then if you talk about proton, it has also a strong coupling, right? So it's 0 to 100, and that is almost like 10 to 40.
Right.
But then if you go for the abundance, like proton is always equi-abundance with the fluorine.
Right.
But in the case of 13C, that's very, very low.
Very low. Very.
If you are talking about a small molecule, so the abundance, would that also determine the
So the good question. Again, thing is the carbon NMR upon is 1.1 percentage. Now suppose a direct bond fluorine couple, it's a doublet. 1% split into 0.5. It's too large. The problem is everything buried under the noise. Now we will get difficulties whether I have a peak or not peaks. If it is, now I mentioned 1. Suppose I have CF3, 3 fluorines are present. It means a quadrant. The one carbon gives a 4 peaks. That's again everything buried under. You will get confused. Suppose I have lot many carbons. This quadrant is like a 200 hertz. One small here, one somewhere here, one somewhere there. Then you will get difficulties whether it's a separate peak, whether it's a coupling one. The really difficult task for the assignment of these carbon structures. Okay.
But that adjacent proton will also make the splitting, right?
Splitting. But in general case, carbon NMR will be a proton decoupled carbon. So like two channels, carbon goes in this channel, proton goes in these channels. So I can make a decoupling. The carbon observation time I can do with the decoupling of the protons. But the problem is fluorine coupling will come in this case. But anyway, I have interesting solution for that. I can show you in the later stage where we can do a enjoy with the single carbon signals with this case.
But the other thing is the CF coupling can be felt like 2-3 carbons away. So the magnitude of the coupling kind of decreases with distance away. And so you might have, a trifluoromethyl, and you see the quartet really clear in the first one, and the second one you get further down, and now you have a fully substituted carbon that's already tough to see. And then you have this quartet, and you're like digging in weeds there to see if there's any.
Yeah. And if it is a peak is merging, then everything is even difficulties. So when it is coming up these cases.
Good students can do it. Good students can do it.
Okay. Yeah. So Gyrometric ratio similar like a proton 1, highly abundance 1. Okay, this is some of the examples how the fluorine chemical shift varies with the a substitution part. Now if you have some just CF3, look at this is minus 68 ppm. Now it's maybe you can say full of shielding or something. Then you have replaced one fluorine with the proton. Again, look at a chemical shift variation, minus 100 ppm. So it's a huge difference. Then replacing with the two protons, the fluorines with 2 protons, it becomes 200. It's a shielding one cases. It's a large separations chemical shift. This is why interesting. Fluorine has one small, has because of steric effect or polarity effects, small changes make in the molecules as can be reflect on the fluorine spectra. It can be seen that. Interesting. Now in here is an aromatic systems where you have in the second rings you are changing the substitution part. Still there is a variation happens with the chemical shift of the fluorines. You can see that when you have a just simple with this proton here, so then you can minus 220 ppms, and if you have with the methyl in these places, then it becomes the minus 313s. There is almost a 20 ppm, 10 ppm difference over here. So this is interesting. Now you are known only about a proton carbon correlation methods. Now I suggest is why can't you do with a fluorine carbon correlation experiment? It's an interesting fact that you can work complete assignment different molecular sites. So this is what I want to say, that small changes in the molecule can introduce a lot of frequency difference between the individual peaks. This can be taken into these cases. So and the solvent effect, that again there comes sometimes your molecule dissolved in different solvents. But in the fluorine case, changing a solvent not makes much difference. If we take most of the case we take a CDCl3 or DMSO or something. Changing the solvent maybe introduce 1 ppm or 1.2 ppm maximum can change. We don't consider as NMR, this must changes happen. But in case of proton, there may be a lot of changes. No, when you take from in this case here in the molecule, look at this molecule you are here, CDCl3 peak minus 76 ppm, but same thing molecule taken with DMSO, it's minus 75 ppm. So the difference is very small over here. But in case of the proton, so it becomes a 582 ppm, and then it becomes acetone becomes a different 1 ppm difference. It is a large difference for the proton cases. So what I want to say is in the solvent changing, the fluorine has not much effect on this, but proton can be seen that effect on the cases. So here, let me go to the examples now here. I have a small molecule over here. Here it is, you can say 1,1 substituted 2,2,3,3 hexafluoropropyl ethers. Now you have a 3 fluorines, 4, 1 here, here. Now if you take a simple proton NMR, how many signals can expected here? In this molecule, how many signals can be expected? Proton signals. 1, 2, 3, but I have shown only 3, 2 here, the another one is somewhere here, and of course it is the shielded area, so I have not shown because I want to show some of the interesting fact here. Now this is how many splitting will comes? This is a one quadrate, okay, because of methyls. But there is no effect transfer because of heteronuclear over here, it won't transfer the couplings over this. Now in the case of this one proton over here, now proton, you see one proton becomes a lot of splittings over here. The why is happening because of this fluorine coupling plus doublet will happens, and plus this fluorine and this fluorine coupling on this proton becomes a lot of complexities. So same thing, if you do the fluorine NMR cases, there are three peaks. One fluorines over here and another two, you have fluorine methyl CF3 protofluorines over huge signal, you can see that shielded one, and you have the two fluorines because of this proton coupling is present. Now you can see this fluorine has behave different, this fluorine has a different, you can say two doublets over here, you can see that. And this is also, there's a, look at the patterns over here, it looks like a, this is called, we call it a strongly coupled spin systems. Some, because when you have a chemical shifter becomes closer and closer, peak becomes same positions. When you have slight variation in the chemical shift, you can say magnetically equivalent or chemically almost equivalent, magnetically non-equivalent, there will be slight variation. So coupling value is higher than the chemical shift, those are considered as a strongly coupled spin system. Okay, this is called roofing effect, or you can call it this. This is, you can feel it here. These two protons, the fluorine case. This is a fluorine. The widespread here, you can see that. Now let me zoom the problem now here. So this CF31 all becomes a huge couplings over here, and this fluorines has this splitting patterns. One is the proton coupling because it looks like this same exactly same replica here. It is a proton coupled. And other effect are this fluorine coupling and this fluorine coupling onto these, it's become the splitting patterns. Okay. Now, if you want to achieve this good resolution side, you should require something like a fluorine with a proton decoupling part. So you can get the only the homonuclear coupling patterns. So only fluorine structure can be seen over here. And this splitting is because of the fluorine couplings. It's not the proton coupling sides. You can see that. So this is basically you can call it as multiplets. It's not be exactly a patterns can be identified.
So during, as you have already mentioned, that one at a single time we can do only one decoupling, right? So when we are doing this proton coupling over here during 19 years, so can't it be 13C will be interfering this?
Yes, it's a good question. Yes, in this case carbons interfere. Now you should tell me that. Now question is, you have molecule complete, right? So what is the carbon abundance? 99% will be C12. 1.1% C13. Yes, in your spectra you have 13C coupled. Unfortunately, the peak is buried under the noise. You have two groups. Whatever you see in a peak, it is a C12 attached to fluorines. Okay? You got it? There are two type of molecules here. One is a 13C attached to fluorine or fluorine. Another one is C12 attached to fluorine. C12 is NMR inactive. That cannot be given. That's a huge peak, 99%. 1.1 will be the C13.
I think if you increase the concentration or if we just record it for longer hours, that might also show up and the peak
it's not required, sir. In the same spectra it is there. I have to zoom it up. If you see a simple proton NMR, you probably see the satellite peak. We call the NMR terminal satellite peaks. Just zoom it up, that's a carbon satellite. Measure the distance, you get a proton carbon couplings. Maybe 150 Hz, 130 Hz, depending on the coupling constant. It can be seen. Yes. In quantification, we always say that decoupled exponent is better one. You have decoupled the carbon over here. Now, okay, you are talking about a fluorine quantification here? Yeah. Fluorine quantification side also, when you do that. So we are taking, this is a peak for the 99% of the C12 attached to fluorines, okay? You are missing out of the 1.1%. That's also contributing for the quantification. Now, when we say that quantification, you have to decouple the carbons. While observation of the fluorine, decoupled with 13C, so that whatever the satellite adds on to the center, that becomes single. So you will get a complete whole molecular area can be seen over here. So coupled spectra is not 100% quantified. Decoupled is a more quantified process.
So when you try to use quantitative, when you try to quantitate with NMR, you need to set your delay time to about 10 seconds. So some of them don't, if you stop it at 3 seconds or 5 seconds, some of the fluorine nuclei will not fully relax, and then you don't get the full signal. So you see like alkenes, if you take a lot of NMRs for like a normal alkene, sometimes those peaks are only 0.6, 0.8. They don't integrate to 1.0. That's because you have not fully relaxed. You have enough time to fully relax. The same thing happens with fluorine. So if you want to use quantitative, you need your D1 to be at least.
So actually in NMR, we we have two separate techniques, qualitative measurement, quantitative measurement. Quantitative requires some special parameter has to maintain. One is major relaxation. Okay. So we always say that ideal procedure is you should measure T1 value of the fluid first, then multiply 5 times of the T1. That value will be your relaxation parameter. Because you are using 90-degree pulse. Again, this order 45 degree. Okay, let me talk about 45 90 degree means my magnetization is in the Z direction. My receiver coil is here. I'm tilting this magnetization to the receiver phase is called the flip angle. Okay, so this is a flip angles. Now what happens when you do normal NMR? These are highly abundant nuclei. But if you apply 90 degree, you should wait the 5 times of T1 to relax back. It's a long time. But qualitatively, you don't want to wait that much of time. What we do is we apply only 30 degree angle, flip angles. Okay, we take the projection of that. That is enough for the qualitative measurement. Okay, but yeah, what is the gain will be the relaxation times are less, maybe lesser times. But quantification, this is not going to work out. You should apply the 90 degree pulse, fully flipping. Okay, then wait all the nucleus to relax back. Then start second pulsing. So this is a qualitative. But how do I know this? Every nuclei has a different relaxation. T1 values, maybe a CF3 may be different, CH2 may be different. Then to measure that, the right method is measure the T1 calculation. The experiment called the inversion recovery method or saturation recovery method, experiment templates. Now these are the robust or it is modern spectrometers. If you want to put a Q and MR, Q fluorine, the recent template is ready. Select the experiment, submit it. Automatically will calculate the T1 first. Then takes the maximum T1 value in your experiment. Then you use last.
I agree with everything. If you go to 10 seconds, you cover all the different fluorine types of fluorine atoms. So that's like the really thoughtful way to do it. But if you just want a program that covers a whole bunch of different types of fluorine, regardless of what's in your molecule, we just say 10 seconds covers it all. So, but that's the right way to do it.
Yeah, this is what to do. That's why the integration when you measure normal, you will not get an exact number of integration numbers. That is because of the relaxation effect in these cases. Yeah, this is the things can be done, proton fluorine. There are some special techniques or the probes are available to do this kind of things. As a first I told, the going of two frequencies, same channel is a difficulty part. Now the recent development from spectrometer in the probe side, where you can handle both the frequency together. Let me go to real problems here. Now I have same molecule, if I measure the carbon experiment, simple carbon, without any decoupling one. All carbons, you need this carbon splits a quadrate because of this fluorine couplings over here, somewhere here, and plus this carbon splits because of this fluorine coupling. And again, this is fluorine also impact on the carbon also over here. There is a couplings over here. This is, you look at this here, lot many peaks plus signal to noise ratio is completely decreased. Okay, this is not acceptable for the regular operations or the assignment strategies. So that's why we do with the proton, carbon with the proton decoupling. So at least you can gain it. But in this molecule, there is no gain for you here. So no, you can apply this proton can be removed over here, but the fluorine couplings will be present. Okay, so you can see, look at these areas over here, a lot of splittings. Now you require something like this, where a carbon, proton, and fluorine simultaneous decoupling, so that I should get all single peaks. Okay, but this problem is there are 3 nucleus measurement. At a time 3 nuclei has to go inside. A routine spectrometer, this is cannot be handled over here. This is case. But yes, there are some special techniques or probes are available to do that. So this probe I hope you have in your facility in these 600 MHz NMR cases. So we need to check that. So but in the 600 MHz this facility where you can do this experiment, carbon with the simultaneous proton fluorine decoupling possible to do that. Okay, so let me just give a brief introduction about spectrometer. I'll go to the again applications now. So we have a very new series of spectrometer called the luminous series spectrometer. So this is how it looks like. Probably in your case maybe a different spectrometer one, the previous generation one, and is a very latest one where you have a most advanced digital and the high frequency technology. And interesting fact is multi-resonance measurement is possible in the standard configuration side. So let me go to that. So like, okay, this is my spectrometer. Now my 2-channel spectrometer I have. 2 channel means channel 1 output, channel 2 output, okay, 1 frequency. Now in this spectrometer, luminous series spectrometers, all that, and especially for the your NIPER instrument also has the same facility. Actually, one output you can apply the 4 frequency. Another output you can apply the 4 frequency. It can be handled spectrometer side. Okay, example wise, if I have something like this, I can have second channel can have carbon and first channel can have proton fluorine together, can be applied. Now let's come to the application side. Of course, here 3 nuclei. To handle that, we require a special probe called Royal HFX probe. Okay, it is basically 2-channel probe, but it can handle the 3 nuclei together. Okay, while observation of the carbon, maybe proton-fluorine decoupling is possible. Or while observing a proton, you can make a fluorine, carbon, both decoupling is possible to do that. It can handle Royal HFX probes. Okay, the Royal HFX probe is basically a 2-channel probe. Channel 1 can take care of the proton and the fluorine, and channel 2 can take care of the phosphorus to nitrogen, completely a broadband range. It can be handled. And in this probe, you can do a temperature range from -100 to +150 degree. You can do that. And tuning and matching is completely automatic. You can do that. And specialized experiment, as I was talking about that earlier, it was not possible, but it is possible, like a proton fluorine decoupling, fluorine with the proton decoupling. Interesting is carbon with the simultaneous proton fluorine decoupling is possible to do that. It's not only for a carbon, you can use any X nuclei, because I mentioned it is LF is basically a broadband. You can use for the any nucleus here, X with the proton fluorine. Now interesting experiment like HMBC, suppose your earlier days proton carbon HMBC means just a proton carbon correlation, but while doing, if fluorine is present, it makes a disturbance. But with this Royal HFX probe, while direct observation, you can make the fluorine decoupling, and in an indirect dimension, you can make the fluorine plus with the proton, both decoupling is possible to do that in indirect dimension. All the carbon gives contour gives a very nice one single contour, plus the acquisition time is reduced much, because the signal to noise ratio boosted by the because of decoupling part. Here. So, okay, here is an example. Now I have some working on his old samples over here. This is basically a drug molecule over here, where you have the aromatic, the 3 fluorines are there, 2 fluorines added in the aromatic, another 1 fluorine is for the heterocycle, this ring. Now if you do simple carbon experiment, now you see aromatic peaks, all the carbon signals becomes a splitted lot of things here. Let me zoom that area, you can see that. Now the 2 problem, one is the splitting is more, second one is signal to noise ratio is very, very less, because 1 peak you can double it. Okay, 1. So this is very difficult for assignment sites. But with this Royal HFX combination, you can do something, this experiment, carbon with the simultaneous proton fluorine decoupling, so that I can remove all the interaction, fluorine and proton interaction, all signal becomes singlet. You can get a very nice singlet. Signal to noise ratio much, much better. For me, that is interesting here. Earlier days, you have to spend for the 5 hours, 6 hours for simple or carbon measurement, and this can be reduced a lot. Plus complexity has been reduced a lot, right? It can, all carbon becomes single peak for this. So same, now I have a small molecule to show that. Okay, this is very simple, the fluorine bromo attachment, chloro attachment for this molecule. Okay, how many carbon signals we expect here? 6, simple 6 carbons. But how many we are getting this? When you record simple carbon, you can see that so many peaks here, too many. This is a simple case I showed. Suppose this same group is attached to some another group of organic groups, then spectra becomes more and more complex here. Now this is basically a 2 peaks. This is because of this carbon fluorine coupling to the directly to this carbon becomes a long range, sorry, 1 bond coupling, very strong. It's maybe a 250 hertz or something like that. Then the one of the peak is no splitting at all. It's because of there is no much. This is a case somewhere. Yeah, sorry.
That intensity is high because it is too.
There is no coupling effect on this group. Basically, is everything singlet. So you can say that fluorine has no basically this is meta portion of the carbons. There is no effect seen onto this carbon. Now you have the 2 peaks. Maybe this is a 1 ortho positions 1, and second one is para positions 1. There is a strong coupling. You see, this peak also got splitted over. If you see, look at, if you zoom that area, there is a splitting. It's a long range fluorine coupling between this fluorine to this carbon couplings. There is a, fluorine has a strong effect onto the multi-bond couplings. I mean correlation, or you can say coupling constants. So this fluorine is not only effect onto the direct carbons, it has impact on the next bond, 2 bond, 3 bond, 4th bond also it can go coupling.
But why doesn't it do in the meta place because of its?
Maybe the electronic density or something. Coupling patterns goes to the bonding electrons, passes through the bonding electrons. Now there is a deficiency or something electronic triggers, so that is not able to see any kind of the effect onto the carbons in this case. There is no effect on fluorine couplings on these cases. So there may be a slight, if you zoom it also you are not able to see it, because the spectral resolution itself is a broader area. Because the line shape of the carbon is quite high compared to the proton bond cases. Okay, relaxation effect. So there is no.
Yes, can you also explain the delta, like that variation and reasoning?
These cases. chemical shift frequencies. Yeah, so it's the fluorine direct bond coupling. It's an electronegative atom, right? This is of course becomes a deshielding, highly deshielded part. So this is very basic. Okay, if you go to this areas, this is called the upfield, or you can say shielded areas, and this side comes to the non-shielded, or you can say deshielded areas cases, right? So when you have electronegative atom attached to these carbons, there is all electrons are pulled up. The carbons, the nucleus becomes more exposed to the magnetic field. It can give frequency, it can absorb more frequencies. Maybe because energy state may be larger compared to the methyl or other cases. So that's why the frequency is a larger area. That's why you can see that 150 ppm carbon signals over here. And splitting is because the fluorine, one fluorine is attached to the carbon, so it gives a, you can say, doublet. And thus fluorine has again 2 bond coupling and good 3 bond also, but again this depends on the bonding network electrons. Okay, all coupling patterns goes through that. So you cannot see it.
Something I see that is the strong intense one, that is actually the meta to fluorine. That is this side, but then the
Yeah, I also feel that. That is what I was thinking. Maybe that the one carbon which is attached to bromine, maybe this is that. That's what you are saying?
No, this is the one basically. You call it. Am I wrong? Assignment?
No, means if we are only seeing the, so there are 2 things. One is, okay, the fluorine also plays roles, right?
Yeah.
That's right. Fluorine also plays roles. We are negating that. So that has also its donate direct. Yeah, exactly. No, that's okay. It's not so common.
I think go to the one last spectra for you. This will be easy. So now you can see this is now where proton fluorine decoupling is applied. So this has become a singlet. Now assignments become much easier for this. Is all splitting goes off. These cases. Okay. So this is can be done with these cases. It's not only 1D. If you want to do with the fluorine and the carbon correlation, now suppose you have these difficulties, we can go to the simple HSQC. 1D is enough, and if you want, you can go to HSQC based one, fluorine carbon HSQC. Okay, and that is will give clear identification. Or you can go to the HMBC, fluorine carbon HMBC. HMBC is basically multi-bond correlation spectra can be done in these cases. So this can be an interesting application can be done with these cases. Now another example over here where you have a phosphorus is present over here. You have triphenyl groups over here, and now 2 benzene rings have the full of the fluorine attachment. Now if I record the phosphorus for this molecule, how many peaks I expect? It should come only 1 peak, right? So because of phosphorus. But if you see, simple phosphorus makes a lot of complexity over here. Why? Because there are 2 fluorine here and 2 fluorines over here, and it becomes, this is again the pentate. You can see if you talk about simple multiplicity patterns, pentate. And plus there are 2 protons are also here contributing to this. This becomes a lot of multiplicity, you can say multiplet peaks, you can say, one complex peaks individually. Now if I do a proton decoupling for the same molecule, I can remove the interaction of this proton onto the phosphorus, then I can see this is a peak spectra. Why this splitting? Because of this 2 fluorine and this 2 fluorines. It is a 1, 2, 3 bond couplings. This is strong enough. It gives a splitting patterns. Now you can do a phosphorus, a proton, fluorine simultaneous decoupling. It becomes a singlet peaks over here. You can see that. So these are the interesting things you can do it with these cases. Like you have a different experiment, like this is basically another experiment for another molecule. It is a proton carbon HSQC experiment. Okay, 1 bond correlation. Now again it makes a complexity when you have a fluorine is present, like similar like a protons, it becomes multiplicity. Then you can do something like, while doing indirect dimension of the carbon, you can do a fluorine decoupling and plus proton decoupling, both together has to do it. You can do that. And direct dimension, you can do the proton observation, but while doing a proton observation side, I can apply the fluorine decoupling so that I'll get all peaks becomes a singlet for that. Contours can be seen this. So this is something interesting experiments where you can do it. I hope you have the same facility, you can utilize that cases. So now I have one of the molecule, same molecule of complete assignment, I have taken that. So you can say, of course it is a published application note from our group, so I have taken the same spectra to showcase that. So it's one of the drug molecule where you can see that. So again you have 2 fluorines over here, fluorine here. If you do a simple proton may be very simple for it. If you record a proton spectra for this molecule, you can say very clear, nice spectra, very easily to assignment that. But this is not enough, and there is not much on this proton. Of course there are proton, but it's not enough proton to showcase that. You require some additional supporting 2D experiment also. Now you see that there is a proton over here, and this proton and this all where you have aromatic sites, this fluorine has a coupling partner. So you can see that the splitting patterns over here and signal to noise is reduced and plus here also. Now you can do a proton fluorine decoupling experiment so that you can remove all the fluorine interactions. Now this protons over becomes, you can see that very nicely. So this is interesting when you can mention that if you do a fluorine decoupling, at least you can identify which areas of this is interacting. It can be seen that. So now here also becomes signal to noise is much increased, and this is the protons of the fluorine coupled area sites. Let's zoom that areas. Now you can see this is how it impact. Now you have the 3 protons over here, and this is a coupling. This coupling is because of this fluorine coupling to this proton. Okay, and same thing, this fluorine is not only here, it can go to impact over here and here also. You can see that here in the cases of the 6th protons over here, you can see it has an impact here. And if you have a 5th protons, again you have the impact on these cases, coupling partners. These couplings can be removed over these identifications. So you record a simple proton and you can do the fluorine decoupling experiment. You can see splitting patterns easily. Identify this, which areas of the proton has an impact, it can be seen. You can go to this.
Those small peaks, that is the satellite and
This one?
Yeah, this side also.
Yeah. This is basically satellite peak has a too large distance. I believe this may be some impurity peaks. You can see that. And when you have coupling, I don't think it comes to very closer. Somewhere it will be here. Symmetric. Both the sides will be symmetric. Satellite peaks. Satellite and spinning sideband. There are two things in the NMR side. Spinning sideband. There are 2 satellite. The downside peaks will comes. One is sample is spinning. Because of sample spinning, you will get a spinning sidebands. It is not a genuine peak. Okay. It's, you can say, instrumental peak. You can say that. And satellite peaks are low Gyromant ratios or carbon coupled one or any other NMR active nucleus coupled to that. That is called the satellite peaks. It comes in the base of the noise in the cases. Okay. If you zoom it, you can see those peaks. You can see that. So now in the carbon NMR also same thing here. Now a lot of splitting over here for the carbon of the molecules over here. Okay. It's very difficult to make the assignment when you have these ones. Okay. You may be required some expertise in that, or you require a lot of time to assignment. But instead of that, we suggest now a new technique has been come up where you can apply all the decoupling. You can identify the simple directly attached carbons one. This carbon and this carbons and again this carbons again. You can identify that very clearly in these cases. And this coupling also we know, you see this is coupling is again the strong long range couplings. It is not a one bond is one, second one is a long range couplings makes another problematics. So noise levels in the, more over here. This can be increased.
yeah, Srinivas, I wanted to do a little bit because there is a doublet of doublet, right?
Yeah.
Then, otherwise, they are like the 2, since like 4 carbons, and now after decoupling,
It's
the only
one. Yes.
So,
Yes.
so that means, so it will be very useful for.
So there is a 2-bond coupling also over there. It's maybe you need to zoom it up, you can see that properly. And this is splittings off because of the 3-bond one. Because we have assigned this is 1D and it's not enough to assign completely whether 2 bond, 3 bonds one. We require 2D experiments to do that. We have a couple of 2D experiments has been performed onto this to final assignment of this molecule. Let us go to this one experiment to identify that which is my proton, fluorine and couplings. We have an experiment 2D called a simple COSY experiment. Okay, COSY is probably the new students just want to introducing. COSY is correlation spectroscopy. If you have a 3 bond, if a simple example, proton, proton, COSY will be done. This you have a 3 bond, bond 1, carbon, another protons. This correlation can be get from the COSY. It's a correlation spectroscopy. But in this case, what I have done the proton fluorine COSY. Okay, so you have something like this, molecule fluorine and here a proton. If you have this kind of connections, you will get the COSY peak for that. This is a correlation spectroscopy. Okay, same thing now in this experiment. The direct dimension is the proton and indirect dimension is the fluorine. Basically, if you do it, it's based on the 3 bond couplings only. You can go through that. So here only wherever these protons are present near to the fluorines will get a peaks. Apart from that, like this is a proton over here and this proton, that coupling will not appear. Again, there are some couplings over somewhere here, it won't come up. Only wherever the fluorine is present, this is only comes up in the pictures. You can say indirect dimension peaks for the fluorine, one fluorine peak for here, one is here. You can see that. And as per the assignment, you can see that this is a fluorines for this one, this ring fluorine, and another F4 and F2. This fluorine and this fluorines one will be here, this one. Okay, and you can see the coupling, but here there is a 2 peaks over it. Is again this whether it is a H4, now it's assignment of this one cases, whether this proton, okay, this is the one cases, this is the proton cases over here to assignment parts, whether this proton or this protons, it's not sure from the simple cozy experiment. Okay, it may be maybe chemical shift wise you can say that whether this is whether this proton or this proton on these two cases, confusions. Then when you do another advanced HMBC experiment, from that you can identify that which is the one proton H4 and H6 cases. So this kind of interesting experiments can help you for the assignment of your molecules. If you sit and properly do the assignment of the individual peaks, then you are able to identify the correlation of these whole molecules. You can identify the correlation parts.
I'm going to ask, where is this most useful? Because if you have the coupling constants, the J values, those tell you which proton is coupled with which fluorine.
Yes.
Also.
That's
so when is this experiment going to be more useful than just matching the coupling constants in the normal 1H and the normal 19F 1D experiments?
Okay. So when you have a simple 1D, if you have coupling constants too strong, the peak may be merges. So when the peaks are merging, the splitting patterns, difficult to identify whether it's a fluorine couplings or proton-proton couplings, or maybe assignment of identify the exact coupling constant, or may be difficult for you to whether it's a fluorine-proton couplings. But when you do the proton-fluorine cozy experiment with the decoupled pattern, so we'll get a separate peaks for you. So that will identify that only in this case, fluorine coupled proton only comes. Other peaks will not vanishes everything. Suppose I have my proton with the fluorine coupled, another one proton is without fluorine coupling, it's merging like this. You know, simple 1D NMR, difficult to identify the coupling constant for this one. Now what I can do, if I do a cozy experiment, I'll get only these peaks for this. Okay, this peak will vanishes. Maybe this one, I will vanish this one, only this peak will comes up. Then I can identify, okay, this proton is coupled to the fluorines or that ring protons. So 1D will make some more complexity. Okay. Of course, 1D can give you coupling values, gives you identification of the whether proton fluorine coupled one or not coupled one. However, when you have complex structure, molecule size is big, peaks are merging up, then the cozy might help you out in these cases. So you can assign this part, and plus we have experiment called the fluorine carbon HMBC. Again, so we all know that a proton carbon HMBC, it's basically a long multi-bond correlation, long range coupling patterns, right? You generally utilize for your experiments. But you can assign an experiment for the fluorine and the carbon HMBC experiment, so that you can assign that. So if the fluorine, as I mentioned, the long range coupling is present very strong, this fluorine can give a chain for this whole things. And same thing fluorine for this carbon and this carbon and this carbon, everything goes. And if it is so strong, this fluorine can give up to this carbon also, it can go to this. Okay, from this you can assign that. So you have, this is basically a fluorine dimension, the direct dimension observation of fluorine as like a proton, indirect dimension is the carbon one. Okay, you will get the cross peaks for all the carbons and the one fluorine cases, you can identify it. So you can make the chain identification for these cases. Okay. If you do assignment, you can easily identify these categories. Experiment is very simple. Multi-bond correlation as a proton-carbon correlation. Similar way, instead of the proton, we can go with the fluorine side to identification these cases. We can identify that proton sides over here. Okay, and the small peaks you are seeing that it is basically coupled. Again, when you do HMBC or HSQC, this works based on the 13C, not a C12. So now you have a center peak, big peak, right? That is no useful. It is completely vanished, because when you do the HMBC, all works based on 13C based one. The small satellite peak is important for you now. Okay, that will give an impact for the HMBC 2D, all 2D NMRs are that. So now this is just an example to show that how the decoupling will help you out. This is no decoupled, makes a lot of splitting patterns, and the full decoupling on the indirect dimension can the single carbon spectra. So assignment becomes much easier for using into your characterization sites. So the next experiment also can be the proton nitrogen HMBC. Okay, so this is also not most utilized. You can use that. Now the proton, carbon, nitrogen, if you do this one, you have, this is basically nitrogen one, you have nitrogen over in the triazole groups, and again here also you have nitrogen one. Now if you do the HMBC one, this one proton is enough to give correlation to here and here this nitrogen. Similarly, this proton can correlation to this two nitrogen, and this also can give to the correlations. Now when you do this one, you can easily identify that. Now we have assignment is made over here, you can see it easily identified. It's basically you have the 4, 2, 1 this ring, and this proton belongs to that, and you can make the assignment for this. Similarly for that you can do this. Let us zoom these areas. Okay, you can see that this is basically of this network nitrogens one. You can see that if you zoom that area, you can clearly identify the individual peak splittings. From that you can identify the individual peaks. Now you can see that where you have the CH2 protons over here, no, this is a protons where you have the 3 bond couplings, 1, 2, 3 bond couplings over here, and behaves it too differently. It separates. Okay, 3CH2 1. So okay, this is a 1, 2, 3, 1. Okay, you can have these couplings one. You can see this. So this is we can make assignment. When you have a nitrogen and proton correlation, proton carbon correlations, you can pick up the experiment. And all the experiments are ready in the templates. You can make that. Of course, the coupling values little bit variations based on the literatures are available. You can input that values, and you can run this experiment for you. And these all are the universally detected or proton based or fluorine based detections. Experiment time is very less, maybe 1 hour, 2 hours, you will get a very good data of this, especially fluorine based carbon correlation experiments. Very fast acquisition can be done with these cases. So this is an interesting one, and again there is a fluorine nitrogen again. You can see that the only this ring will give a correlation, but here nothing. It is basically a direct dimension of fluorine and indirect dimension nitrogen experiment. You can get this is a correlation peaks over here. 2 nitrogen peaks can be seen. This is you can identify when you make a chemical shift chart. You can identify the chemical shift values for that. So there are interesting experiments is available in NMR for utilization for this complete structural characterization can be done in these cases. So finally, I will not go into detail about all the things. Maybe you have experts you can discuss, or maybe there are plenty of literatures available on this all individual experiment to know more about it. So one of the last, before completing that, I want to come up with this experiment. It is called the LRHSQMBC. It's one of the very recently developed, we can say. It's not so new, it's 2021 or something like that. Very interesting, it gives a very weak coupling also can be picked up. You can see that is the ring mentioned over here. This fluorine can contribute to the long range couplings can be seen very clearly. Very nice contours, very high sensitive can be seen that, singlet noise ratio can be seen this. You can do it for the direct dimension will be a fluorine and indirect dimension will be a carbon. Now why we preferred here it is that sometimes what happens is the coupling between this and the long range is very weak. Okay, that cannot be picked in the normal HMBC. HMBC will not give. When you have again 2 bond, 3 bond has a confusion. Plus long range will not be picked up. But LRHSQMBC uses specialized pulses, adiabatic pulses and different methods, and you can get a all correlation. Long range coupling can be seen in this LRHSQMBC, and this pulse program is again ready with your system. And you can take any modern spectrometer, this is easily available. You need more information thus. So I would like to conclude my presentation now. So I have used, this is a guide, so very nice for the fluorine NMR identification. You can go through this book and you can get a plenty informations. And in YouTube also you can get a plenty of YouTubes on that fluorine NMR. Thank you very much. Yes. Okay. If you want to take it. Yeah. If you have, I can share that also books with you.
Yeah, I think I've already shared this with me.
Okay.
And maybe can we share this with the students with the books of I think you shared this book with me. The PDF long back.
I don't know.
I think about 1 or 2 months back.
We'll talk stuff, yeah. I don't know.
I can also share this.
I have this. Okay, I think this was a wonderful again talk where we learned about many aspects of fluorine NMR. So any questions? Yeah, we already have some discussion in between. So I think if there are no more questions, so we should thank. I think you have something.
Maybe I have one suggestion or one thought for people. A lot of times in methodology, you might be able to include a fluorine atom on your substrate or as a handle to use NMR for rapid screening.
monitoring as one of the interesting bomb pattern.
Can you please again, I missed that.
So when you do fluorine chemistry, it's easy to monitor, and your goal is to make a fluorinated compound. It's easy to monitor conversion, yield, things like that. But if you're doing a methodology and it's not fluorine specific, say you're just doing a Suzuki coupling or some cyclization chemistry, if you put a fluorine atom somewhere else that's not the key bond you're trying to construct, you can still use that as a handle to monitor conversion and yield quantitatively using the NMR. So, we do that sometimes. We're trying to do a certain reaction, and we're trying to make a fluorinate over here on the molecule. We might put a second fluorine atom on the far side so that we can differentiate starting material, intermediates, product A, product B. Even though we're trying to do chemistry over here, we can still track what's going on with the rest of the molecule by another fluorine atom.
Yeah, great. I think the monitoring is with the fluorine NMR is much better than the GC because we don't put your fluorinated compound on a GC.
It's not
recommended. Yeah.
You don't have to use a deuterated solvent. So you can take your reaction solvent straight into an NMR tube and run your experiment. It's really easy.
Yeah, so just we should thank Srinivas for coming.